pretty exciting as we get into our introduction to trig here. So chapter 11 is going to be just looking at a high level of trigonometry. We're going to get into some of the concepts, but we're going to keep it again kind of at that 30,000 foot level. I'm going to see a few different functions. So we're going to see sort of our sine, cosine, tangent functions, which doesn't mean anything to you now, but it will in a little bit. But we're going to stay pretty centered around those. Again, just kind of giving you the gist of things, especially focusing on right triangles. But I will mention a few other topics. So some of the content today is going to be beyond what I would expect you guys to be doing, like for a test or just within this chapter in general. But I do at least want to expose you guys to the ideas. So we're going to start out talking about a couple different things. The first thing I want to talk about, just to get out of the way, is these Greek letters. So these Greek letters here, the first one here is alpha, the next one here is beta, this one here is gamma, and this one here is theta. So alpha, beta, gamma, theta. Alpha, beta, gamma, theta. So when we're using these variables, this is just to name different angles. It really is pretty unnecessary, but it's like cool to use these funny letters, so let's use it, right? So we got some Greek letters, we'll throw those in there. We're going to talk about just our intro today, which is going to include our sine ratio, but we will talk about all of the ratios. So when I'm talking about trigonometric ratios, trig ratios are basically just from a given angle, a set of ratios. So this set of ratios for sine is going to be the opposite side over the hypotenuse. Again, this doesn't mean much to you now, but let me just kind of get it out of the way. We have these cosine ratios, which are adjacent over the hypotenuse. And then we have these tangent ratios here, is opposite over adjacent. So just to give you an example of what this would sound like, I would say sine of, and then I would say an angle like 10 degrees equals, and then some number. So let's say sine of 10 degrees, I'm going to just punch it in my calculator real quick so I can say some actual numbers. Sine of 10 degrees is approximately 0.1736. Okay, that means nothing to me other than the fact that that's some ratio, right? It's one thing over another thing, it's a fraction. It's a really messy fraction, but a fraction nonetheless. So when we look at this, we have sort of the sine, cosine, and tangent as our different functions, and they each use a different ratio of the sides of a triangle. So the reason that this is important is because we want to talk about our similar triangles. This triangle here on the left and this triangle here on the right are similar triangles. We can get that similarity through angle-angle. We can also get it through side-side-side proportionality. So we have two similar triangles here. If the two triangles are similar, all of their angles are congruent. So all of the ratios of these angles would be congruent as well. So let's say, for example, I was doing 3 over 4. That's 3/4. 6 over 8 is also simplified to 3/4. So my ratios are the same. If I had any size triangle and you said, okay, well, let's keep all of the proportions the same, but let's make it bigger or let's make it smaller, right? So we're just scaling this thing. All of the angles are going to remain the same. So that's why all this trig stuff is useful. If I'm able to look at a flag post and say, okay, well, I have to kind of crank my head up at 40 degrees when I'm standing, I don't know, 50 feet back to look at the top of the flagpole. And then we say, okay, well, what if somebody makes a super huge flagpole? It's like 600 feet tall or whatever like that. And I were to back up a certain number of feet, then what angle would I look up at that flagpole at? And so again, it's going to be the same as long as the ratio is the same. So that's why when we're looking at all of these things, we can say sine of an angle is this thing, or cosine of an angle is this thing. So when we're talking about these different ratios, there's a way we kind of have a little tool here to help us remember what each of them go with. And again, this probably is all a little bit confusing and overwhelming at this point, and that's okay. Just kind of bear with me through this high level stuff, and it may be something you want to revisit later on. But we have this term SOHCAHTOA. So there's a kind of a funny story that goes along with this. Let's just say there was a mathematician back in Portsmouth a while ago who was discovering trigonometry, and they were working on solving the trig stuff. And as they were doing all this math, they would get really hot, and it was in the middle of summer, so they would want to kind of just go down to the water and just cool off a little bit. But the water around us is really, really cold, so although it's very, very hot out, the mathematician only needed to soak their toe in the water just to cool off. So the name that this mathematician got dubbed was SOHCAHTOA. SOHCAHTOA standing for sine, cosine, and tangent. So is sine, which is opposite over hypotenuse, right here. Ca, which is cosine, is adjacent over hypotenuse, right here. And then we have toa, t, tangent, which is opposite over adjacent. So when I reference so, ca, toa, that's what I'm referencing. It's just a way to help us remember what the ratio of sides is with each of these trigonometric ratios. Jumping to the left here, there's this weird overwhelming circle of values, okay? This is what's called our unit circle. In our unit circle, we can draw any triangle we want, and then we can scale this thing up. So within the first quadrant is basically where we're going to be living, but I do just want to mention this circle to you. In this circle, all of our adjacent sides are going to be our x values. So that's why our x's corresponds with cosine. All of our opposite things are our y values, and that's why it corresponds to sine. Now the reason for that is that my radius in a unit circle is 1. So I see this point here, from the center of my circle out to here is a distance of 1. From the center of my circle up to here would be a distance of 1. I'm going to erase that just because writing over the 90 here. So when we look at this, a unit circle of 1, if I did any one of these things, opposite over hypotenuse, well, the hypotenuse is just 1. So it's just going to be the opposite thing. So that's why my sine value is the y value, and my cosine value is my adjacent value, my x. So we're going to live in this first quadrant here. We're going to basically just deal with 90-degree triangles, and we'll go to some other stuff a little bit later on. But for right now, that's where we're going to focus. These are just the nice values that are derived from an equilateral triangle and also from a square. If I had an equilateral triangle and I bisected one of my angles, I'd be able to get this 30-degree angle here. And we've seen this root 3 over 2 and 1/2 before. And we also get to this point here where we see 1/2 and root 3 over 2. So just the flip version of this, whether I'm doing my 60 angle here or my 60 angle up here. 45, 45, 90, we see from dividing a square from the corner to corner diagonally, and we see root 2 over 2, and that's because I'm saying my radius is 1. So we've seen these before, although this may look like it's in a little bit of a different form to us. When we're going around the circle here, we're looking at the cosine value to start. So when I'm looking at cosine value, my cosine value starts here at 1. As I go around the circle, I reach 0. As I continue around, I go to -1. Continue around, I go back to 0, and then continue back around to 1. And then I repeat that cycle. That's why my cosine graph looks like it starts at 1, goes to 0, goes to -1. Whoops, I guess I'll do that on the actual graph itself. Goes to 0, and back to 1. This is beyond the context of what we're going to be doing in class, but I do just want to have you guys have an understanding of what these things are. When we're talking about the circle in terms of radians, radians is just a different way of dividing the circle out. 360 degrees is nothing special. It is approximately how many days there are in the year. That's how the number originated, as a number of degrees in a circle, to do one full rotation around the sun. So when we're looking at a circle, it's much more useful to talk about it in terms of radians than it is degrees. We are not going to do a lot with radians, but I just want you to, again, be exposed to it. So jumping back up here, if I did the same thing for sine values, starts at 0, goes to 1, to 0, to -1, to 0. We see that graph right here. So these things form these nice sinusoidal graphs. These sinusoidal graphs look like this, right? They look like just squiggly lines, and they follow this consistent pattern. Sometimes they're a little faster, sometimes they're slower, sometimes we move them up or down, and there's all sorts of cool stuff you can do, but that'll be more in your trig class. We're just doing intro to trig. So as of right now, just to summarize what we've covered so far, we have trigonometric ratios, which are just a ratio of the sides on a triangle, right triangle. So we're just focusing on right triangle trig. So when we look at these things, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So now let's look at actually labeling those sides. This gives us a good view of how we want to view these things. When we're looking at these triangles, almost all of them will be named triangle ABC. We'll then use alpha for A, beta for B, and gamma for C. Why do we do this? I don't know, just because it's fun to include Greek letters. I don't have a better answer for you than that. When we're looking at these things, the side opposite from the angle gets that same letter with a lowercase. So my angle is uppercase A, whereas the side length here is lowercase a. Likewise for B, likewise for C. When we're doing these, 9 times out of 10, the C angle is the 90-degree angle, although it doesn't need to be. We can call this thing whatever we want. Name it CAT, name it DOG, whatever you want. Just keep in mind that the uppercase, lowercase is a pretty standard notation. When we're looking at this thing, when we're naming our sides, so when I'm talking about hypotenuse does not change, right? In a right triangle, it doesn't matter whether I want to focus from starting at point A or focus from starting at point B. The hypotenuse is C regardless. So just keep that in mind. The hypotenuse doesn't change no matter what your vantage point is. Now, the reason I'm talking about vantage point is that when we're looking at sine, cosine values, we're talking about for a specific angle, right? Sine of 10 degrees is some number. Sine of 20 degrees is some number. Cosine of 30 degrees is some number, right? That's how all these things work. It's just a ratio of the sides. So when I'm looking at this first one here, I just want to imagine I'm putting my perspective. So I like to reference the little mall star maps, right? If you go to a mall, there'll be this little like map thing sitting in the middle of like the food area or whatever. They'll just be kind of like smattered around the mall, and it's got a star and it says you are here, right? So that you are here star is what I'm using to reference this angle. So I'd be talking about sine of alpha, cosine of alpha, tangent of alpha from this point here. Now from this point here, this is my opposite side. This side A is opposite from this angle. This adjacent side, which means next to this angle, would be B. The hypotenuse is always going to be across from your 90. So from this vantage point, from alpha, this is my opposite, this is my adjacent. If I wanted to talk about my cosine value, I'd be doing adjacent over hypotenuse. So it'd be B over C. So it would look something like this. So I'll just do one example here for you. Cosine of alpha, which is like a fish swimming to the left, equals, and now here again I'm just doing my adjacent over my hypotenuse. So let's say we had some values here, call this one 10 and call this one 12, it'd be 10 over 12, right? Cosine of alpha is 10 over 12, and we could actually find what that angle is by doing the inverse cosine, but we'll get there. So this is just an example of what this looks like. Now if I change my position, right? So I went to a different part of the mall, I'm standing in a different location. Now I'm referencing from this point here, my adjacent side is side A. My opposite side is side B. So if I were to write out an example here for cosine of beta, which is like B with a tail, then I'm just saying, okay, well, it's going to equal A over C. And that's it. Again, fill in some values here, and we'd be able to work our way back depending on what was given to us. So the first one we're going to look at today and focus on is sine. So in my sine ratio, sine is the SO part, the first part of this SOHCAHTOA, so we're focusing on this part here, is opposite over hypotenuse. Now in this one, again, I'm just going to say it depends on what I'm referencing. A here would have opposite of A over H, my hypotenuse, my C value for my hypotenuse. But if I was referencing beta, B here, then B would be my opposite and C would be my hypotenuse. So it's going to depend on where we're stationed. So here I want to find the sine of alpha and the sine for beta. So when we're doing sine of alpha, let's do that one in red. So looking at sine of alpha here, I want to start by just drawing my mall star map, and I want to label these things. This is my opposite, this is my adjacent, and this is my hypotenuse. From here, I'm going to say, okay, well, what is my sine ratio? Sine of alpha is going to be my opposite over hypotenuse. That's all it is. So that is going to equal for us 3 over 5. That's it. So my sine of alpha equals 3/5. For beta now, I'm going to switch it up. Mall star map goes here. Now this is my adjacent side. And now this is my opposite side. This is still my hypotenuse. So looking from this perspective, now I want to do 4 over 5. So sine of beta is going to be, oops, I'll do the adjacent. Oops. Opposite over hypotenuse here. That's pretty trash handwriting. Let's fix that up. All right, opposite over hypotenuse, that's better. And here we get 4 over 5. So that is my sine of alpha and sine of beta values for this triangle here. Looking at example 2, we're going to find sine of alpha and we're going to find sine of beta for this right triangle. In this, the only thing different from the last one is that we'll have to solve for our b value. Nothing crazy. This is a right triangle. We still have Pythagorean theorem. Like, there's nothing different than what we've done so far in the past. So if I look at this thing, I'm basically going to say, okay, 5 squared plus b squared is going to equal 13 squared. So I would set this up right here. And then from there, I'll go ahead and solve. So my b value is going to equal 12. Now that I know my b value, I can start doing sine of alpha and sine of beta. So let's use our mol star map right here for beta. And let's use our mol star map right here when I'm talking about alpha. Now for alpha, again, this is my adjacent. This is my opposite. Here is my hypotenuse. So here, again, sine being opposite over hypotenuse is going to be 5 over 13. For the next one, we're doing beta. So here I want to label my hypotenuse, opposite, and my adjacent. So here I'm going to do 12 over 13. That's my sine of beta value. I'll just talk to this for a second. Here it talks about the measure of the acute angle and figuring it out. I'm going to explain how to figure it out in a minute. It gives you an expression like here it says it's being 53 degrees, has uniqueness. So basically it's just saying like type sine of an angle and you'll get whatever the ratio is, or if you have the ratio you can figure out the angle. But we'll get to more of that in a second here. I'm not going to put a ton of emphasis on this example here just because I'm not going to be super concerned with exact values. The reason being is that we're not going into depth, so we're just going to keep it at a pretty high level. So here's just an example showing you if I have a square with side length x, then if I cut that with a diagonal and I was looking at the right triangle that was created, so here I have a 45, 45, 90. If I wanted to figure out what these lengths are, I would start out with that ratio. So again, it doesn't matter if I had like, say I have this triangle, call this 3, 3, and 3 root 2, and I've got another version of this thing where we're going to say it's like 5, 5, 5 root 2, right? So in both of these cases, this is a 45-degree angle, this is a 45-degree angle, this is a 45, and this is a 45. So in solving this, we can work our trig magic here to figure out sine of 45 degrees is, and then do the ratio. So just simplifying again, here I'm going to just put my mol star map here, although it doesn't really matter because it's the same angle for both. But I'm going to label my opposite. Here's my hypotenuse. So if I wanted to do the math out here, I have x divided by x root 2, which is going to give me 1 over root 2 when I simplify, because the x's are going to cancel off. So now when I'm looking at this thing, I'm saying, okay, well, I want to rationalize, so I want to multiply this by root 2, whoops, not a very good 2, root 2 over root 2. Again, just don't want to have any radicals in my denominator. So this becomes root 2 over 2. And that is what this value for x is right here. So looking at this, what would my hypotenuse be? Well, I'd multiply by my root 2, and so here it would just be just like our unit circle had. So just tying this all together for you, if this doesn't make 100% sense. I'm more okay with that. More concerned that you'd be able to just find the 45 degrees if I gave you these lengths, or if I gave you this 45, that you'd be able to fill in one of these missing lengths here. Again, this definition is going back to our unit circle. Basically just our sine of 0 value is 0 and our sine of 90 value is 1. This is our first quadrant, so this is our chunk of the circle like this. So as we came around the circle, this point here was 1, 0. This point up here was 0, 1. So in looking at both of these values here, I just want to look at the y's. So y is my sine. So yeah, I see that sine of 0 is 0. Sine of 90 is 1. Cool. So again, just tracing back to the unit circle, this is by definition, if you want to just use a calculator for it, that's fine. Again, I'm not really requiring you guys to know all that much about the unit circle as of right now. We want to find the length here. We're going to suppose, so for sine 15, we're doing opposite over hypotenuse. So here's where we're going to actually start plugging in and solving for these things. So again, if I take one of these pieces out, you should be able to find the missing one. So looking at this one here, if I give you sine of 15 degrees, I'm giving you this vantage point with this angle, right? The 15 degrees I'm giving you is right here. So this is going to be my opposite. This is my adjacent, and here is my hypotenuse. What does sine use? Sine uses opposite over hypotenuse. So when I'm setting this thing up, I'm going to say sine of 15 equals a over 10. So a is the value I'm solving for here. So if sine 15 equals 8 over 10, there's two ways to do it. This says from the table. Okay, boomer, right? So back in the day, this was the best way to grab all of your sine, cosine values. We are not going to be utilizing this. It's somewhat interesting, I guess, if you want to look at it, but I don't really want to spend the time of referencing a table when we have a calculator that can do this thing for us. So I'm going to tell you in 1 second here how to do this part. So basically, on your calculator, there are 3 keys: sine, cosine, and tangent. If your calculator doesn't look exactly like this, the TI-84, that's fine. The TI-30 has the same setup, so it's basically just 2 rows above the last row of numbers, the 7, 8, 9 there. If we want to do our inverse functions, that's where we're going to hit second, and then it'll be inverse sine, inverse cosine, inverse tangent, but we haven't quite gotten there yet. So for right now, just identify this as sine, cosine, tangent. If I press this button with my finger, and then I hit 15, and then hit enter, it will tell me what sine of 15 is. So rather than looking it up on the table, I would just do sine of 15, and my calculator spits out approximately 0.2588. Call it good. Cool. Oh, it matches. Awesome. So looking at this now, we're saying, okay, so this number, which is messy, which we're going to leave it as an approximation, is going to equal a over 10. So how do I get the a value? I'd multiply both sides by 10, and I'm good to go. So my a value equals approximately 2.588. Now, personally, what I would do is I always will solve for the variable and then have the calculator thing be my last step. So when I'm doing this, it would look like this. It would look like sine of 15 equals a over 10. I multiply both sides by 10. So I get a equals 10 times sine of 15. And that's exactly how I would enter it in on the calculator. That way I'm not having any rounding issues here. So personally, if I were doing this, I would say my final answer would be 2.5882. But again, if it says round to the tenths or round to the hundredths, then all that accuracy doesn't really matter. But again, just trying to emphasize the difference between an approximation and the exact value. This is an exact answer. 10 sine 15 is perfect. If I were asking you this on a test, that's what I'd be looking for. So just keep that in mind. If I ask for an approximation, which I will on this test in areas, then, just round. It's pretty easy. Plug it in, good to go. But otherwise, I just want you to leave it like this, and that's totally fine. Looking at another example here. So again, this says use a table or use a scientific or graphing calculator. Just grab the calculator. Save yourself the time. So here, just find sine of 36. So what am I going to do? The keystrokes here are a little bit deceptive. It depends on what your calculator is. Most calculators are going to look like this. So again, with the TI-30s and the TI-84s, just again, it's the sine key first as your keystroke, and then 36, and then enter, and it'll give you your answer. Versus what it's referencing with scientific calculators in degree mode, this is like if you, I don't know, say you have a Casio calculator or something. I don't know. I'm just trying to think of like what calculators use this. It'd be like a little bit of the lower end scientific ones, or maybe it's Casio, because Casio just seems to make life a little bit harder than it needs to be. So looking at ones like this, depending on your calculator, it could be that you have to type in 36 first, and then you hit the sine function. I would not recommend doing this on your phone. If you don't have a calculator on your phone, then you can download the Calculate 84 app, which is free and is a 84 emulator. So works pretty well. That's what I would recommend, but you do you can get away with it on the calculator. On the phone, I'm pretty sure if you flip to the side, it will give you the trig functions there. Let me see. Yep, yeah, so it does have the values. So on the phone version, just keep in mind that like one keystroke off is gonna like throw things. So yeah. As we look at the next example here, we're just saying the same sort of thing. Can you find this value? But here I want to go in reverse. So here I'm going to introduce the idea of that second key and then the sine thing. So I'm just going to give you an example. We're going to use this exact example here. So we're going to use this one where we're saying sine of theta equals 0.7986. Okay, this is the thing that I want to solve for. How do I unsine this thing? Well, what I have to do is I have to take the inverse sine. A lot of people think of this like division. If you want to think of it like division, I mean, whatever helps your brain, but we're taking the inverse sine. When I do it to the left side, I have to also do it to the right side. So now I'm going to unsine this thing. So I just get theta by itself, which is what I wanted, equals, and here's my inverse sine, which I'm going to tell you in one sec how to do on a calculator, of 0.7986. So now I'm going to jump back up here. Here's where if we hit the second key, then we're accessing the little thing written above it, right? So now if I do second and then hit sine, I'll do inverse sine. So on my calculator it says sine -1, and then I want to punch in my 0.7986. When you do that, it will spit out an answer for you, which is theta equals, and typically when I do this, I'll write like approximation because it's not exact, but you know, close enough. Let's see, 0.7986 gives us 52.9966, which if we're rounding to, you know, even the hundredths place, we're just going to round this to 53. So that is how we would find our theta value. So again, if I have sine of something, cosine of something, tangent of something, to undo that trig function, I want to take its inverse, right? So inverse of sine here will cancel off the sine. Do it to both sides. So on the right side, I'm doing inverse sine of, and whatever that number is. And that'll give me my theta value right here. Here is just, you know, me really flexing my artistic abilities. When we talk about trig stuff, we often will use these two terms. One is angle of elevation, and the second is angle of depression. Angle of elevation is when we have a baseline, so this is like the ground here, and then the angle which is created looking up at a certain point. So this would be from this vertex on the ground. This can also be from a person's eye level, so that's going to be in the picture I explained here, but it's just this angle here, right? So this is my fixed side, and then I'm looking up however many degrees. So this angle, let's say, is 30 degrees, right? My angle of elevation here would be 30 degrees. We can do the same thing. Here we're using an angle of depression. So here I'm starting out saying that this is my flat line. Now I'm coming down, I don't know, say I come down 20 degrees there, right? So this is an angle of depression. Here's an angle of elevation. Now, when I look at these things, here's a person standing on a cliff. They're looking down an ice cream cone down here with a cherry on top. And they are sad they cannot reach that because the cliff would mean certain death for them to jump off here. So they're going to have to find some other way of getting the ice cream. So their eye level comes out here. And then the angle which is created looking down to the ice cream is the angle of depression. Here, from the ice cream's perspective, it's elated that no one's eating it. Its elevation, angle of elevation, is looking up to that individual right here. So this angle getting created here and this angle of depression here look to be awfully similar to me. If I were to create a set of parallel lines from this individual's level of sight here to the ground level, those two things would be parallel. So when I create a transversal line that runs through like this, these are alternate interior angles. So my alternate interior angles here are congruent. So that's why these two things look so similar. Let's do an example. So here we have a tower. It is 200 feet tall. Keep in mind that when we're talking about height, we're talking about the vertical, just straight from the ground to the top, not the distance from the ground to the top. And there's a wire that connects a support. Okay, so this will come in a lot of different flavors, but here's one of them, right? So antenna that goes to the ground that connects it, right? Okay, cool. That's one way of saying it goes from the top of this thing to some point out here. So just keep in mind there's going to be a number of different ways this can be phrased or presented to you, but it's different than the actual height of the thing. So now looking at this, I want to figure out what this angle is. What's the angle of elevation? So to look up and see the top of this thing, how hard do I have to crank my neck? And again, this is a little bit of a weird example just because it assumes we're standing directly at ground level, but a lot of things will do this. So looking at ground level here, you know, if I wanted to start at 6 feet up, then it'd be a different problem. But looking here, I want to figure this thing out. Well, to me, it looks like I'm using, this is my vantage point. I have some information about my opposite side. I have no information about my adjacent side, but I could figure it out. Again, with this being a right angle, I have Pythagorean theorem here, so I can figure this out. It's just a right triangle. Here's my hypotenuse. But I'm lazy, I don't want to figure out things I don't need to. So when I look at this, I'm saying, okay, well, sine of, that always happens, sine of alpha equals my opposite thing over my hypotenuse. So here's going to be 200 over 250. And now I'm going to do some math here. Inverse sine is going to get this thing by itself. If you want to simplify this, you can. I mean, I don't know. I personally would not, but go for it if it makes you feel better. So we can simplify this thing. Otherwise, I would just do inverse sine. So inverse sine of the left side means I'm going to do it on the right side as well. And that's going to equal my alpha value. So I'm doing inverse sine of 4/5 here, which is the same thing as doing inverse sine of 250 or 200 over 250. So let's see, inverse sine 200 divided by 250 gives me 53.13 degrees approximately. So to the nearest degree, so here I'll say my alpha value is approximately 53. I'm just going to write 1301, but my final answer here would be 53 degrees if I'm rounding to the nearest degree. So again, just taking the concept of having that sine ratio and using my opposite side that I know and using my hypotenuse that I know to solve for this distance here. Or excuse me, the angle here, not the distance. And that is a wrap up for our intro here. I will leave off with this. If today was confusing, please try and rewatch the video and go over this stuff a little bit more. Tomorrow is going to be basically the same, just using a different ratio. So instead of focusing on sine, it's going to focus on cosine. So just keep in mind that this is the general concept. It will be rehashed in the next like 2 lessons. But if something is totally off tomorrow, revisit the stuff today because I go more in depth today than I will in the next lesson. Just FYI.